Hello everyone and welcome to Fiddlestack. Frida is great, but modern RASP is getting better at detecting it. So to stay truly stealthy, we have to operate where the detections are not looking. We are about to use Renef framework to hook native functions in real time. If you haven't seen the intro to this framework yet, check out the previous video first. Otherwise, grab your terminal and let's start tracing some native ARM64 logic. Now, before we start writing Renef scripts directly, we need to know exactly what we are dealing with. So in the previous video, I have showed you when we tried to attack this application using Frida, it was able to detect it and showed hook detected error message. But with Renef, this was not the case and we were successfully able to attach our hooks to this application at Java layer. So for this video, I have already extracted GarudaDefender application using APK tool over here in my working directory. Let's head straight into this directory and go inside libarm64 where we can see all the native libraries used by this application. And it contains two native libraries. One is libcrackme.so and other is libkickypspro.so. This is the core RASP engine, and this is perfect for our demonstration of native hooking. It contains simple imported functions like strcmp, dlopen, etc., which we can trace or intercept. So let's start with native hooking then. And for that, let's quickly open this libkickypspro.so into Ghidra disassembler to see what all imported functions are there which we can trace. I have already opened this native library into Ghidra and currently it is being analyzed. Okay, so once the analysis is done, inside this symbol tree window under imports, if you expand this external list, you will be able to see all the imported methods which are coming from some other system libraries. And over here, we can see a lot of interesting functions such as fwrite, getPID, read, strcmp, strcopy. So we can try hooking on strcmp or strncmp as these functions could be used to compare some sensitive strings. Now, if you remember from the previous video in the beginning, I told you that Renef supports two ways of hooking. First one is using PLT or GOT pointer redirection. In this type of hooking, instead of touching the actual function code, we just swap the address in the redirection table. It's incredibly clean because the function body remains untouched. However, there is a small catch. It only works for imported functions. Then the second way of hooking is using inline trampoline. This approach actually modifies the function body in memory. We go right into the function body and replace the first few instructions with a jump to our code. It's powerful because it works on any internal function, but it leaves a footprint. If the RASP has a real-time memory integrity check, it will see that jump instruction and shuts us down. So let's get hands-on with PLT-based hooking. To see how to implement this inside this Renef documentation, let's head over to Lua API reference section. Here all the functions are neatly categorized and we are looking for hook API section and to hook. So the name of the API to hook native functions are same as what we used for Java hooking, which is hook. But for native, the arguments are different. For hooking native function, this hook API takes three arguments. First one is the name of the library whose function you want to hook. Second argument is the offset where the target function is located in your target library. Then the third one is of course the callbacks, which is a function body in which you have on enter and on leave callbacks. So without wasting any time, let's create a new file. Let me just go back to my working directory, which is Renef framework demo. And over here using vim command, I am going to create a new file called native underscore hook.lua. Enter. And instead of typing everything out, let me just copy and paste this code snippet. And now let's adapt this snippet for our target. So the first parameter is the target library where the function we want to target resides. In this case, let's say we want to hook strcmp function, and on Android, this function is present in a system library called libc.so. So this is something you need to know first before applying PLT GOT based hook. So in this case, I am going to leave the first argument as it is, which is libc.so. Then the second argument is the function offset we are trying to intercept. Now you don't need to manually disassemble the libc.so file and check where the strcmp function is located. That would be very tedious. Instead, Renef provides us an API which allows us to enumerate all the exported symbols from any native library. So if we go back to the documentation and under Lua API reference section, there is this module API, right? Inside this, we can find all the APIs related to modules. So over here, we have this API called module.exports. This will allow us to do exactly what we want to do. That is finding exported symbols from any loaded native library. And this API takes one argument, which is your target library name. Here, two code snippets are mentioned. First one will basically print all the symbols from the native library, and the second one will filter the symbols and help us to find a specific function, and this is what we want, right? So let me just copy this second code snippet and paste it into our script. Before this hook, I am going to list down all the exported symbols from this libc.so library. Now let me quickly explain what this code snippet is doing. Basically, using module.exports API of Renef, it's going to return a list of all the exported symbols from libc.so. Okay, and because it's a list, we have to iterate over it, right? So for that, we are going to use for loop, and then with the help of this if statement, we are going to filter down the list of exported symbols. So in our case we are looking for strcmp method, right? So let's compare the symbol name with strcmp, and if it matches, then only we are going to do something. So first of all, for better visibility what's going on, let's just put this print statement which says strcmp, and let's print its offset, which we can get using this symbol dot offset. Okay, now once we find our target method, then only we want to attach our hook, right? So let me just move this hook API call after this print statement. Okay, now coming back to the second argument of this hook API, like I mentioned, it takes an offset where we want to attach the hook, right? So here, instead of passing the offset manually, we are going to pass symbol dot offset, which we have managed to get using this module dot exports API. Now for the actual logic, the third argument, which is the function body, is where we define our on enter and on leave callbacks, right? Since we are targeting strcmp method, we know that it expects two arguments. First argument is the source string, and the second argument is the string it's being compared against. So inside on enter, let me just change it from malloc to strcmp, and then in the second print statement, let's just intercept these two arguments as s1, and instead of hexadecimal value, I want to print it as a string with the help of %s access modifier. Similarly, to print second argument, we can put s2 %s as access modifier, args1 to access this second argument. Now, unlike Java hook API where the first argument is in args2, in native hook, args0 contains the first argument and args1 contains the second argument, and so on. Now we don't want to modify the arguments, so let's just get rid of this, right? And once the function finish executing, only callback will trigger. So inside this callback, instead of malloc, let's just put strcmp and print its return value. As you might know, strcmp returns an integer based on comparison. So if the string matches perfectly, it returns 0. So instead of hexadecimal value, let's just print it in the form of integer using %d access modifier. And as of now, we don't want to modify the return value, so let's just get rid of this as well. Now you must be wondering how Renef will differentiate between PLT GOT based hook and a normal hook, because the hook API is common for all hook types. So the thing is, by default, Renef uses inline trampoline based hook. So if you use this script as it is, it will use inline trampoline mechanism internally. But for now, let's focus on PLT GOT based hooking. And to explain it how it works internally, think of PLT, which stands for procedure link table, and GOT, which stands for global offset table, as the GPS of a native library. Since functions like strcmp live in external libraries like libc.so, our kickypspro.so library doesn't know their exact memory address at compile time. Instead, it uses a relocation table. So when the app calls strcmp, it first jumps to a small stub in the PLT section of the native library. This stub looks up the real address in GOT table. By using Renef in PLT GOT mode, we are not modifying the strcmp function itself. We are simply poisoning that GOT entry. We will swap the real libc address with our own hook address, and the app will think that it's going to the system library, but it's actually diving straight into our script. So to tell Renef to use this mode, we have to add a new parameter called caller. Like I mentioned, it jumps to a stub in PLT which resides inside the same library from where we are trying to intercept strcmp method. In this case, it's kickypspro.so. So what we have to do is inside this hook API, we have to add caller attribute and provide the caller library which is calling this strcmp method, which is libkickypspro.so, right? Now, one more thing I forgot to mention is that by default, this args0 and args1 argument contains the reference pointer, not the actual data. So we have to read the data from that memory address pointed out by these args0 and args1 variables. And to do that, we have memory dot read string API. Because we know it's of type string, we can directly use read string API. Alright, now we can save our script. So in the previous video, I showed you how to use Renef's interactive shell. While the interactive shell is great for debugging, in a real world assessment, we want speed, right? So this time I am going to skip the interactive shell and I am going to use a one-liner to attach our hook. This is the most efficient way to load your logic and specify your hooking engine in a single command. Before launching Renef client, we have to make sure that Renef server is running on the device. So let me go to another terminal and via ADB shell, let me take root permission. So Renef server needs to be launched as a root user. And under data local temp directory, I have Renef server located. Enter. Let's go back to the previous terminal. Oh, and one more thing. Before trying out this PLT GOT based hooking technique, make sure you update your Renef repository because we have made some changes into the way this PLT GOT hook work internally. So make sure you are running the latest updated version of Renef. Let me just clear out this terminal, and before launching the Renef client, let me share my device screen as well so that you can see what happens. Now the device is visible, and to attach our native underscore hook.lua script using one-liner, we have to launch Renef binary, which is under Renef build Renef. Then just like Frida, to tell Renef which script to use, there is this -l argument which takes the script name, and then to spawn a new instance of the application we have -s command followed by the package name of your target application, which is com.kickyps.trackme. And before launching this command, let me tell you something. To observe early native hooks, currently Renef client has some limitation. Sometimes it's not able to show you the logs in your interactive shell in real time. We are working on this as well and it will be fixed soon. But meanwhile, what we can do is we can look at the hooks whether they are triggered or not using ADB logcat. And over here using ADB logcat command, I can see the complete logs generated by the device. So to filter that out, I am going to pipe it to grep command and going to see only the logs generated by Renef. Enter. Alright. And now let's run this command. Enter. And in the logs, now you can see the logs generated by Renef, right? Let's go at the top, and over here you can see that it's using PLT GOT based hooking method. So this confirms that Renef is using PLT GOT based hooking method. And then you can look for these strings function called. So when you see this section, it means that your on enter callback got triggered, and with the help of this script tag you can see the logs generated by your script. So in our case, if you remember, inside on enter we have printed strcmp called, right? Then after that we have printed both the arguments S1 and S2 of strcmp method, right? Then we have our onLeave callback triggered over here, and you can see the return value as well, right? So this method got triggered multiple times, and you can see the strcmp method call and the values or the argument. Okay, so that's all about PLT GOT based hooking method. Let's move on to the next section, which is inline trampoline hook. So let me first clear this out. Let me also quit the Renef client. And if I go back to our script, and if I remove this caller, Renef will fall back to default mode. But unlike PLT method, this time we aren't touching a redirection table. We are modifying the actual code inside libc.so in memory. When you apply an inline trampoline hook, Renef goes to a very beginning, which we call the prologue of the function. What it does is it will take first few instructions and save them elsewhere. And in that place, it injects a jump instruction that forces the CPU to leap out of the original function and straight into our Lua script. Because we are modifying the code segment or the text section of the library, this is where modern RASP solutions are most likely to catch us. And many security solutions perform this type of integrity checks by scanning first few bytes of common functions. So from the script, we have already removed the caller argument, and now inline trampoline method should be used by Renef. So let's save this script and let's test it using the same one-liner. But before running this command, make sure you run adb logcat command. Enter. And now we can launch this Renef CLI. Enter. And immediately you can see that hook got detected. So in the logs, if we scroll up, we can see that this time hook type was auto selected as trampoline, right? And no hooks or no callbacks from the script got triggered. And this is exactly why understanding your hooking engine is so vital. By using the inline method, we physically modified the text section of the library. The app's RASP engine performed a background integrity check. Notice the instructions modified by the inline trampoline method inside the prologue of the function and caused the app to crash. Now, some of you might remember my previous video where we bypassed integrity checks using Frida. If not, then I would recommend to watch that video if you are interested to know how to bypass such checks. The core logic is the same. We need to find exactly where the library is reading the .text section of our target binary. If the RASP calculates a checksum by reading its own file from storage, we have to intercept that read call. Now it's your turn. Take the principles we discussed from previous bypass series and see if you can ultimately bypass it using Renef. If you get stuck or have some questions, feel free to discuss in the comment section below. Staying updated on this security landscape is key, so don't forget to subscribe to the channel for more deep dives into native security.